So it's my pleasure this morning to introduce Dr. Eltahir today. He's the H.M. King Bomabol Professor of Hydrology and Climate and Professor of Civil and Environmental Engineering at MIT. Professor Eltahir is a fellow of the AGU, and he's received AGU's Hydrologic Sciences Award. He leads MIT's research group that's focused on how changes in regional land use, land cover, and climate may affect water availability, extreme weather, and spread of vector-borne diseases, all topics of interest to us. Today, Professor Eltahir will be speaking to us about regional impacts of climate change. So let me turn it over to you, and let's go ahead and get started.
Okay, good morning and good afternoon, or maybe good evening to some of you too. It's a pleasure to be with you here and to share with you some perspective on regional impacts of global climate change. Thank you, Lloyd, for inviting me to share some of my thoughts on this topic with this group. So the picture that you see is a picture that describes actually observations of levels, the most extreme levels of heat stress that have ever been experienced anywhere. And you see here, there is a belt between the Persian Gulf and East China that basically stands out as a hotspot for extreme heat, and we are going to come back to that. It's contrasting that with the idea of global warming brings in the regional dimension to climate change. The next figure here is the icon for climate change. This is the observations on carbon dioxide levels of the coast of Hawaii, and they show this persistent pattern of never-ending increase in CO2 levels. You could pick this, you could download it up to the last month, and you will see things are just rising, which points to the fact that even if we choose not to do much about mitigating and addressing this problem, that problem doesn't go away. It's very stubborn. It keeps becoming more intense. But it's not only CO2 that's really of concern. This is also the methane concentration increase, and so it's a similar picture, even a little bit worse. Other greenhouse gases are showing similar trends, we know that this increase in concentration of greenhouse gases is caused by human activity. This is here the rate of emissions of carbon dioxide as estimated from the Global Carbon Project, and it sees that the rate of emissions is actually keeps going up. You know, if you look at decadal time scales, and that's of concern. Even you see the recent dip because of COVID, but now things started going back to normal in the following year. So with increasing emissions, you know, this is an indication that the problem is actually getting worse. It's not getting better. And that observation of emissions and concentrations taken together with the documented increase in global temperature, about a degree or so per century, that already happened, is show this picture of temperature rising everywhere, and that's basically is the cause and the effect of this changes in the chemical composition of the atmosphere. When scientists around the world try to when scientists around the world try to reproduce these observations using the best of models from many centers around the world, the only way you could reproduce the observed record, which is shown here in black, the only way you could do that is by acknowledging the fact that the concentration of these greenhouse gases is rising. And when you do that, the average of what the model simulates mimics reasonably well what has been observed. And actually, if you ignore the increases in the concentrations of these greenhouse gases, the model were not able to reproduce the observations. So the only way you reproduce the observations is if you include the fact that the chemical composition of the atmosphere is rising, which is, to me, is the main evidence that there is this. So it's not only we observe the cause and the effect, we also, like, this is the only way we could simulate it and understand it. And then when people look into the future, we look at different scenarios of what could happen, and the worst scenario is a business as usual scenario, which is like, you know, closer to like continuing similar. It's something similar to RCP at 0.5, and then different levels of mitigation. You know, in my view, the most like optimistic one is if we succeed in something like this RCP 4.5 kind of scenario, that would be a success. But you could be very optimistic and like think even that maybe in the future we would be able to have negative emissions. So this is the range of action that global human society could take, and what effect they will have in terms of what global temperature is going to be, range of global temperature values is going to be. So this is up to now is pretty much a global consideration of the problem. And when people look at every time we do this exercise of like having different scenarios and then trying to see what gets realized at the end, and you look in hindsight, you find that what had been realized, which is here in crosses for different scenarios, has always been closer to the worst possible scenario, which is an indication that we as a global society are not taking this problem seriously. We make all these forecasts, we look at all these reports, and then when you look at what materializes in terms of actions on the ground, they are really very close to the worst possible, which is more closer to something like business as usual. And when, according to this report that was cited in the New York Times, when you ask people around the US, you know, will global warming harm people in the United States? You know, majority says yes. And when you ask them, will global warming harm you directly, personally? Most of them basically say no. And so that most people think climate change will harm Americans, but they don't think that it will happen to them. And so there is apparently this need for better informing people of how climate change is going to impact them at local and regional scales. And that's something that what my group specializes on. The story that I would like to share with you, I'm going to summarize it in this slide, and then I'm going to share examples, and I will leave it for you to really extract these 2 points that I have in the story and how you see them to be relating to the specific examples. The first point on my slide or my story is projecting impacts of climate change on processes that people care about at regional and local scales exposes risks from climate change more clearly and hence better inform local society. So the global focus is not enough. So I hope that through the examples I'm going to show you, you would realize that climate change is really a phenomenon that relates to people intimately in their local settings, in their local systems that are important to society, and that some of what we have done in research really will help inform the local society about these impacts. The other piece of the story is that what we discovered, and this is something we didn't fully anticipate when we started this, you know, a couple of decades ago. In doing so, we discovered that all climate change impacts are local. Some of you are familiar with the saying, all politics is local. So here I say all climate change impacts are local, meaning that incorporating this local context, meaning the natural, economic, political, and social context, not only not not only simply downscaling to higher resolutions, which is what people try to do, that this process is critical for understanding the risk from climate change to local societies. So here the idea is that climate change is not happening in a vacuum. It's happening and impacting people within a set of complex processes that have their own dynamics that are happening in society in different corners of the world. And so understanding the climate change would require not only running these GCMs and like downscale them, but also some effort in understanding the dynamics of the local problems that people deal with. And so these are the two aspects that I would like you to be able to see through the set of 4 examples that I'm going to present. And so the examples I'm going to present, and I'm going to be, brief in each of them. I have much more information in each of these examples that you could really access through my website. My website to start with is eltahir.mit.edu. It's just my last name .mit.edu. These examples include agriculture in the American Midwest, heat waves in Asia, malaria in Africa, and water in the Nile. And each and every one of these topics is really topics of critical importance that I'm going to show to you, to society in general. So if we start with agriculture in the Midwest, closer to home here in the US, I think what's happening these days with the Ukraine war and the impact on food markets and production of wheat and export of wheat and so on, exposes people to the idea that agriculture is really a critical sector. We used to, for a long time, take food and food prices for granted, and so because of the success in agricultural productivity around the world. But agriculture is a very important economic activity, I think, in the American Midwest. And so understanding what's going on in that sector is important. Here is data I start with from Illinois, one of the best hydrologic data set that we have. And what it shows here in dashed lines is the rate of evaporation that happens, the seasonality of it. And you have very strong seasonality in evaporation from the American Midwest with the peak of it during summer. Precipitation is plentiful in this region of the world. And so you see here precipitation, you get rainfall, significant rainfall almost every month. And that rainfall exceeds evaporation during winter and spring, during fall and winter, but it really lags evaporation during summer. And so you have what we call P minus E, a quantity that I would like to bring to your attention. P minus E is the difference between precipitation and evaporation, which is during summer is negative. During winter is positive, meaning that water is converging in the atmosphere towards the Midwestern US, towards Illinois, while water is diverging from that region during summer. And so during summer, the soil, and you see here the change in the storage in the soil moisture and the groundwater, you see it in these curves, it becomes negative, which indicates that the soil moisture, the groundwater are busy during the summer supplying moisture to the atmosphere while they get recharged during winter. So this quantity here, P minus E during summer, we think is a very important variable to think about because, if climate change impacts this quantity here, the climatology of this P minus E of this, moisture divergence significantly, then that could have significant impacts on agriculture in the US, a very important agriculture region, not only for the country, but also for the world as a whole. So we focus in our studies on the climatology of this variable P minus E. And if you look at precipitation in summer in the American Midwest, and you compare what happened during the early parts of the 20th century to what happened during the late 20th century, we discovered something very interesting. We discovered that precipitation has really changed during summer significantly. It did increase significantly, as shown here with these statistically significant changes. But also at the same time, and here we are talking about climate change and global warming, what happened during summer in the American Midwest is actually the temperature did cool down, and it cooled down significantly, you know. So instead of it's a warming, we have a cooling effect. And so when you take this region and put it in the context of other regions of the similar northern mid-latitude regions, you see that mostly in mid-latitude regions, what has happened, it have been some warming of a small magnitude, less than half a degree, and precipitation really didn't change much. So this is really looking at a belt 30 degrees to 60 degrees northern latitudes. When you look at this region of a specific interest for us, the Midwestern US, this is the region here that's shown here in dashed blue. If you look at that, you see the nature of the change that happened during the 20th century is actually a wetting, more precipitation, and a cooling, and a cooler temperature, which is quite significantly different than the norm that you see in northern mid-latitudes. So the question is why? And we think that the reason for that has to do to this phenomena that happened during the 20th century, significant intensification of agriculture because of successes in use of better seeds and fertilizers and better management. This region here that you see here in this corn belt that you see in the Midwestern US have been quite productive, as you could see here. So the productivity, not the area, the productivity, which means how much you produce per unit area, has increased by factors of 4. And so that intensification resulted in significant increases in rates of photosynthesis and significant increases in rates of evaporation, cooling down the temperature and providing moisture. The atmosphere, through energetic process, was efficient in making use of it and producing more rainfall. So here we came to look for signatures of climate change on the American Midwest, and we see signature of agriculture intensification instead of climate change. So if you compare what you would expect, for example, in changes in precipitation as a result of climate change from models like CMF5 and so on, what you see here is the picture on the left, and what you expect from intensification of agriculture, you see it on the right. And that's why when you compare the PDFs for what has been observed, which is here in gray, you see it is closer matched by what you would expect from intensification of agriculture. So, however, looking into the future, looking into what could happen in the future, and here we have to rely on CMF5 and CMF6, the models that are used in climate change studies, the GCMs. The models are projecting that in CMF5 and now actually in CMF6 too, they are projecting significant drying that could encompass this region of the American Midwest, significant drying that will happen during summer. So the models, in fact, are showing increase in the amplitude of the seasonal cycle, where springs are getting wetter and summers are getting drier. So that's a result that has to be watched and has to be monitored and has to be understood because I was saying earlier, the P-E could be a very critical variable. So while agriculture intensification, during the 20th century resulted in historical wetting of the soils, climate change is likely to result in a small drying. But given, so how do we handle that drying? Another important feature emerges for this region is that land drainage. Lots of this area in the American Midwest actually in the past used to be wetlands, and it was drained around the 1930s, and a lot of it now is being utilized for agriculture after drainage, using these tiles that basically drain the soil to significant depths. So in this context of current drainage networks and current lack of supplementary irrigation, there is significant room for adaptation to climate change that would really match needed drainage in some areas, additional drainage in some areas, reducing the drainage in other areas, and maybe potentially some supplementary irrigation that would be needed in the future in order for us to be able to handle this projected drying in summer, small drying in summer, and the wetting in the spring. So that's the story really for agriculture in the American Midwest that I would like to share with you. And it highlights this regional and local context that's important to understand. You know, none of the climate models had this, for example, land drainage and how its role in really shaping the hydrology of this area. There is a need to understand, you know, the background of agriculture intensification and how it resulted in wetting. And the need to understand that this area that's now agricultural productive, a lot of it in the past used to be wetlands. And so, so if climate change brings some drying, that drying has to be understood in the context of the historical environment for that region. If you look at the best data, best recent data, for example, and things like, I'm sorry here, and things like precipitation, stream flow, soil moisture, groundwater. This is the data from Illinois I showed earlier. For the recent past, the data doesn't show much trend actually, which is an indication that if climate change is going to bring anything to this region, it's something that's going to happen in the future, maybe toward the end of this century. So the next topic I would like
could I ask a question before you get to the next
yeah,
topic?
I think, yeah, if you prefer that way, that's fine with me. Yeah.
Yeah, and then so I'm assuming that from what you've indicated that with the newer CMIP 6 models, they are not incorporating any significant change in agricultural development. It's kept relatively constant, and so any of the kinds of historical shifts that you talked about that might occur in the future, they're not considered in any of the even in the SSPs.
Yeah, some of the CMIP 6 models have representation of like agricultural and land use changes and so on. The models that are shown here, this is the pure impact of climate change. This is the pure impact of climate change. But even the CMIP 6 model that has land use change, the phenomenon that we think is pretty important is this phenomenon here, which is the intensification of agriculture, which I don't think is something that had been included in models. Maybe very few of them, but not broadly included as an important process. So the land use change has different aspects to it. It has basically conversion of natural land cover into agriculture. There is, that's one category, rain-fed agriculture. There is irrigation, that's another activity. And then there is this intensification of agricultural productivity through processes that enhance photosynthesis, enhance productivity, and in doing so, increase rates of evaporation and impacts the hydrologic cycle. So this specific process is not included.
All right, thank you. And Paul has a question in the chat. With the draining of the wetlands, did this also change the types of vegetation, such as from trees, wetlands to pasture? And if so, what impact has that had?
That process is actually, the draining was with the purpose of converting the natural land cover into more of agricultural productive land cover. So basically into farms. So this is how the history of this farming in the American Midwest. In many areas, the natural setting was wetlands. And I assume that within the wetland protection laws that exist now, you cannot do what was done in the past, in the 1930s and so on, where wetlands were drained and the land was converted into farmlands, and following that, subsequently became one of the most productive lands on earth. Actually, this region is amazing in terms of how agriculturally productive region compared to other parts of the world. But if you think about it from the perspective of drying and climate change, this is not a region where you would worry much about dryingness and basically because the region is naturally, it used to be just a wetland, and so there had to be some management, a combination of like maybe additional drainage, supplementary irrigation, and so on, things of, tailored locally to meet conditions in order to adapt to the future. But I think that would be technologically quite feasible. Okay.
Thank you.
Okay, so let's move to the second example, which is very different. Let's talk about heat waves in Asia. And again, this is something that's in the news in the last few days. Even tomorrow, I think I have an interview with someone from Bloomberg from New Delhi about heat waves in that part of the world. So heat waves in Asia is a significant problem. And let me start by showing you the variable. Let's talk about the variable that we use to describe heat waves. And usually when we think of temperature and we think of heat, we think of temperature as what we call the dry bulb temperature, the temperature that you get from a thermometer. What you really need to think about is that what is another variable that we have been working with, is the well bulb temperature. And the difference between the temperature and the well bulb temperature is that the well bulb temperature measures temperature for this wetted bulb, a bulb that kept wet. And in doing so, it gives an integrated measure of temperature and humidity. The well bulb temperature is defined as the temperature that an air parcel would attain if cooled by evaporating water into it until it saturates. So if you think about it, it's a function of both air temperature and humidity. And the human body, the interesting thing about the well bulb temperature, why do we choose it, is because if the temperature that the skin of a human body approximates the well bulb temperature, it tends to approximate the well bulb temperature. We naturally equipped to cool our bodies through mostly perspiration. There is conduction, radiation, convection going on, but perspiration, which is and the evaporation of the sweating that our body produces, that's the main mechanism by which we cool our bodies. And that you could see here why the skin temperature of the human body approximates the well bulb temperature. In order to balance the metabolic heat generated, we need to get rid of the heat that we generate at a rate of about 90 watts per meter square. And if the well bulb temperature becomes high, our body could not do that efficiently. And so it's assumed in general that 35 degrees centigrade, which is a skin temperature of 35 degrees centigrade, or a well bulb temperature of the air of 35 degrees centigrade, is the critical threshold beyond which the human body cannot get rid of heat. And so that's what threatens the survival of a human being. So you could think of this 35 degrees centigrade well bulb temperature as the critical temperature that we would like to avoid in order for us to survive on a natural environment without air conditioning. To give you a reference, even in the most uncomfortable days that we experience here in Boston or in mid latitudes in general or anywhere on Earth, the temperature would be the well bulb temperature would be more like 22, 23. If the temperature is that way, it would be very uncomfortable to walk outside. So 35 degrees is very extreme heat. So, if I just have to show you quickly the map that I showed earlier, this map, which is the map of the distribution of the maximum well bulb temperature that ever observed. The well bulb temperature that, what we show here is if you take the modern record of observations anywhere and then you basically look at what is the maximum 6-hour well bulb temperature that has ever been observed, and you plot it, and that's what's being plotted here. You see that the maximum 6-hour values ever observed are in the order of 31, 32 degrees centigrade. And there is a region, there is a hot spot compared to the rest of the world that's shown here, blown up blue. And it's a region in Asia that extends from the Persian Gulf, and the area around the Persian Gulf is the warmest. And there is this crescent here that shows in the Ganges and the Indus Valley And then you have Eastern China. In a series of studies in 3 papers, we did focus on the Persian Gulf area, the South Asian region, and in East China to understand exactly how these regions emerge as basically hotspots for climate change. So if I go back here to my slides in their order, so you see here in the area around the Persian Gulf, there have been significant increase in the wab temperature in places like Tehran, Abu Dhabi, Riyadh, and so on, that the wab temperature is really rising recently, and that the maximum annual value is really hitting very high values in the order of 32, 33 degrees centigrade, which is very extreme. So in order to study this problem, we use a class of models which we call regional climate models. We have our own model here at MIT, MRCM, that has been developed and validated through a series of studies done in my group, by myself and some of my students. So we, before applying this model to study the area around the Persian Gulf, we tested the model significantly to make sure that it reproduces observations. And for example, here, this is the albedo, which is a very important parameter for desert environments around the Persian Gulf. And you see, this is the SRB, that the NASA satellites estimates of the albedo for this region. And this is the values for the albedo that the model uses. And so we carefully tailored the model to be able to represent these local processes that are important. And then we looked at how the model simulates this critical variable that the wab temperature. So here you have in the observations, and this is in the model, and these are the differences. So I just want to show you evidence that our model is, before we use it to make these projections, we test it and we spend a lot of time in developing and refining models. And so after we do that, we published a paper in Nature Climate Change in which we made projections for the future under different scenarios. This is the RCP 4.5 I told you about earlier, the RCP 8.5, which is the close to business as usual. And it shows projections on how conditions of this maximum wab temperature to be observed, how they are going to evolve into the future, and under the business as usual scenario, how they are going to approach and exceed this threshold that I talked to you about, the 35 degrees centigrade. So you see, in the current climate, that has not been like, that's extreme, has not been seen. But when we look at how the future under the closer to business as usual, you see that the area around the Persian Gulf, that's really happen in several locations. And if you focus on specific locations, for example, the cities around the Persian Gulf, Dubai is a very popular destination. You see here the PDF for this wab temperature under current conditions in blue, under RCP 4.5, which is significant mitigation, and then under the RCP 8.5, which is the business as usual, and you see significant exceeding of this critical threshold of 35, which we define as the threshold for survivability. That happens not only in Dubai, but also it happens in Doha, it happens in Tehran, Bandar Abbas in Iran, and Bandar Mashahir in Iran too. So it's a significant occurrence, and it has to do with the warm temperature that's of the water of the Persian Gulf, which is already high and is going to get hotter in the future. Combined, in principle, the reason that this region is picked up is not only the availability of moisture, plentiful in this area, but also the low elevation. If you think about it, the Persian Gulf is a big valley, and so as you go down, the temperature becomes significantly higher in valleys. If you think of places like Dubai and Doha and so on, these are rich countries with plenty of electricity and air conditioning, and so it's already in summer. Actually, conditions get pretty uncomfortable, and we're talking about future summers where things are going to approach this threshold. But people here have the capacity that to really handle that heat by use of air conditioning, with a few exceptions. And one of the exceptions is that this region, which is the area in Southwest Asia, is also a region where you have Hajj, the Muslim pilgrimage that happens there every year according to the lunar calendar. And so sometimes it may happen at times of the year where things are basically pretty warm during summer. So we focus on that, and we were able to like project how climate change is going to impact that phenomenon and how extremely dangerous heats are going to be experienced. And that's important because for this pilgrimage that should happen, outdoors and so on. And so air conditioning cannot be the mitigation strategies there. So with that, so again, you see here, we looked at agriculture in the Midwest. This is heat waves in Asia. Local context is important, and even further, this is the map that I started by showing earlier. We just looked around the Persian Gulf. In another study, we looked at this region here in India and Pakistan, and did a similar modeling exercise. And you see also historical RCP 4.5, and when you hit RCP 8.5, which is the business as usual scenario, you see that there is a crescent that emerges here in the Indus in Pakistan and the Ganges in northern India and Bangladesh, where things are warmer and approaching these dangerous heat levels. And as we speak, this region of the world is experiencing significant heat waves. But what's interesting now, the same crescent here, the same valley where we identified that the hazard from climate change is maximized, is a region that stands out as one of the densest populated areas on Earth. So around a billion people or so living on this crescent here. And these are some of the poorest people on Earth in terms of GDP. They are actually poor even by Indian standards, like compared to other regions of India, and also mostly working in agriculture. So here you have relatively poor agriculture or farmers, many of them, who are vulnerable to these significant hazards. There is co-location of the hazard from climate change and the vulnerability from the socioeconomic conditions. So again, the idea that this local context in terms of political, social, natural, is very important when we think of climate change, and especially when you see how climate change is too often discussed in terms of like lowering the global temperature into 2 degrees, or expecting a warming of 2 degrees or 1.5 degrees, while real processes that's going to impact people are happening at really regional and local scales related to specific phenomena like the one we just discussed here. So that's the second example. And now I could take a question or two if you prefer, Lloyd, or
yeah, that would be great. I have a question, but let me open it up for the audience if there's any questions on the heat wave examples. If not, the question I had was on the projections that showed, using the regional model. Do you also include potential changes in land use and land cover? So including some of the urban areas that you referenced.
That's actually a very good point. One of the things that we discovered, especially in northern India, and when we looked at the example of eastern China, is that another process that's making things significantly worse is the process of irrigation, because irrigation actually contributes to enhancing the intensity of heat waves. We are talking about humid heat waves here. We are familiar with the idea that irrigation, basically over irrigated areas, is cooler because the temperature is cooler because of the evaporation. However, that cooling is associated with significant increases in water vapor. And the increases in water vapor content are having more significant impact than the decreases in temperature. And so these regions here that are selected, like the Ganges, some of the reason is because of the irrigation. These are irrigated lands, and so that makes them even worse in terms of humid heat waves. And that process is even more significant as we have seen it and looked at it carefully in eastern China. The North China Plain, which is a very significant region of China, actually, this area here, the North China Plain, is a very significant region with a very high concentration of the Chinese population, many of them farmers. Over there, irrigation, which is very intense and had been there for a long time, plays a significant role in picking this region as a hotspot for heat waves in the future. And so land use change and its impact is a secondary process that around the Persian Gulf, water was available naturally. These are towns surrounding the Persian Gulf, water body. But when you come to the Ganges and the Indus here and also northern China, it's really the existence of irrigation makes things worse. And that was something that we included in our study.
Okay, thank you. Any other questions before he goes to the next topic?
I have a question.
Oh, great, thank you.
Hello. So going back to this particular chart, right, where you are saying that there is a high impact when there is water vapor in the atmosphere.
Mm-hmm.
What is the reason for that? I mean, I can understand where there's a lot of irrigation also means a lot of evaporation.
Yeah,
over from the irrigated canal.
Exactly.
Right?
Exactly. It's the release of water vapor due to irrigation. So you have a lot of water vapor, and so our usually people think of irrigation as cooling, which is true. It does cool the temperature, but it also increases the water vapor content. And
but how does it adversely affect? That's really where I'm going. I mean, what is the root cause? You would think water vapor in the air at some point in time will cause more rain, right? And in itself should help.
Yeah. But water vapor, as I showed earlier here in this picture, the way human beings are programmed to get rid of heat, to cool down, is through evaporating of sweating. And so if the atmosphere around you has a lot of water vapor, the sweating process, the evaporation of the sweating from the skin is less efficient. It's more efficient if you are in a very dry environment. That's why deserts are not hot spots for like let me show you here. For example, the capital of Saudi Arabia, Riyadh, historically and in the future, the water temperature is not high. And that's because it's very dry. And people who live in desert environments, like for example, the southwestern US. In the southwestern US, it gets very hot, but it's also very dry. And so you could spend time outside, and if it's too hot, then you would sweat, and the sweating would cool you down. While we here living in the northeastern US, if in August and July, when we get those very hot days, it's very uncomfortable walking outside because of the humidity.
Right. I see the effect on the human body. I get that. So you're saying relatively how hot we feel because we don't sweat and as such don't cool the body. So you feel hotter when there is more humidity.
Exactly.
Okay.
Exactly.
So, but I'm sorry, go ahead.
And eventually, the impact on human health comes through that process. I mean, if it's very hot, and dry, you get rid of the heat, and the human body, basically the skin temperature cools down, and the human body doesn't care much after the skin temperature cools down. But if you are in a humid environment, if the skin temperature doesn't go down, and if it starts reaching these high levels, then you start interacting with the physiology of the human body, because you can't get rid of heat. So what would the body do with the heat? And at a certain point, it's just like it becomes a problem.
But will it have an effect on the agriculture in itself? That's really where I was going. I mean, I understand the discomfort for the human body. I get that. But
on health.
Environment.
Yeah, I think on the agriculture, what it does, we have done a lot of work on that in the past. Changes in land cover, changes in land use, they have impacts on temperature, on evaporation, and on rainfall too. And so they could have some impacts on rainfall depending on the setting where you are in. Okay, but the focus here on heat waves is really the focus on health. And so on health, on health, it have these negative impacts. On other aspects of the environment, it may be beneficial to have irrigated lands.
Thank you.
So, the third example, and very quickly go through it here. This is an example where, coming from the health area, where basically, as with COVID, people have seen how health and how health impacts and how it really depends on context where you look at that. And so one significant health issue that's mostly in tropical regions is malaria, and malaria has a big hotspot in Africa. It's killing, like, for example, 2018 is close to like 400,000 people, most of them children, and there are more than 200 million cases. So that's why when people started looking at health impacts of climate change, malaria stood out as a disease that we need to understand better how it gets impacted by climate change. And the relationship between malaria and the environment has two dimensions to it. One of them has to do with temperature. And so there is a temperature range that's really ideal for malaria, that's shown here. And the temperature range where the mosquitoes could live long enough to basically to satisfy the time needed for the development of the parasite within the human body. So malaria is caused by a parasite, and that parasite has a cycle. Part of it within the human body, part of it is within the mosquito's body. And so for that development of the parasite within the mosquito, the development of the parasite within the mosquito, the time it takes is function basically of temperature. And so it goes down as the temperature increases. The lifespan of the mosquito is also function of temperature. So for malaria to flourish in a region, that typical lifespan of a mosquito has to exceed what's needed for the parasite to develop within the guts of the mosquito. And that happens within a temperature range of about 27 to 35 degrees centigrade. So that provides a nonlinear and significant link between malaria and its occurrence and environmental conditions, mainly temperature. The other factor that's important, breeding of those mosquitoes occurs in water bodies that are provided by rainfall. So this is here the rainfall seasonality in Niger in Africa. And this is the cases of malaria in hospitals in different 3 years. And you see here, like early on as a hydrologist, you were taught if this is the rainfall, you'd expect this to be the runoff, the river flow. But this is actually the rainfall, and this is the mosquito cases. And so that exposes this other link that, mosquito develop, it takes some time, and then malaria occurs, and that basically provide a link between availability of water and the occurrence of malaria. And so in order to study this process, in my group, we had started a major initiative in Africa where we went out and instrumented a couple of villages in Niger. Niger is that hotspot for malaria in Africa. And we collected their data on everything that relates to malaria: water pools, mosquitoes, adult larvae stage, but also existence of the parasite in the blood of children, done in collaboration with CERMIS, which is a branch of the Pasteur Institute in Niger. And similar to that, we developed a new class of models that basically combines the hydrology, the entomology, and the malaria transmission process. So this is a computer code that has representation of hydrologic processes leading to the formation of water pools, has representation of the life cycles of the mosquitoes and how the mosquitoes breed in these pools, and then go and transmit the disease between humans and different humans. And then when the mosquitoes bite human, the response of the human body to that mosquito. This is a very sophisticated code that provides it's a virtual reality on how the disease transmission takes place. And when we were hit first by COVID, I wish then that we had a model of this sophistication simulating the transmission of these viral diseases unfortunately, we didn't have one, and I don't think we have one even now. So this is a model that simulates not only the natural environment in terms of the hydrology, but also the mosquitoes as entities, simulate them as particles that are moving, attracted by CO2 plumes from human breathing, and also some brave enough to represent some the immunity and of the human body and how it reacts. So if someone gets bitten by a mosquito and get exposed to the parasite, that improves their level of immunity. So for the next bite. So so we tested that model significantly in its ability to simulate the water bodies. For example, these are observations in pictures of where the pools have formed. And here you see in blue where the model projected that pools will form. We looked at how the models simulate numbers of mosquitoes. We captured the mosquitoes, we captured them and we count them. And so we could see how they vary from year to year in response to natural variability. We also simulate how, basically the relationship between the biting rate by mosquitoes and the prevalence of the parasite in the human blood. Because of this extensive testing, and I have written a whole book on this that's available for you to look at in detail. Because of doing that, we were able to simulate how environmental conditions, rainfall, and temperature, how they relate to things like R0, which is this reproduction number that everyone now knows about after COVID. The reproduction number is lower when the temperature is high and the rainfall is low. Especially in this region, and so when you have basically the temperature warming up, that's not good for the disease. Having more rainfall, that's basically enhances the transmission. We looked then at West Africa. This is what the models are projecting for temperature, how much warming of temperature is going to happen in the future, and this is how the models are projecting. The GCMs, the climate models are projecting how the rainfall is going to change. So we take the temperature change, the rainfall change, and we combine them with what our model is saying, how the disease would respond to rainfall and temperature. So that's how we come up with our projection of how malaria is going to change when the climate changes. So the region to the left here, things are getting warmer and drier. So that's basically, you don't worry about increases in malaria here. You worry more when things are getting wetter. But when we looked at these subregions here, warmer and wetter, but the warming dominates, killing the mosquito and no emergence of malaria. That's what happens in the fringes of the Sahara Desert. The warmer and wetter next to it in region 3, but the two opposing mechanisms and no change. So basically the wetting increases malaria, the warming reduces malaria, no change. And when the wetting is really strong, is happening in this region 4 here, warmer and wetter. The warming helps the parasite develop faster, but it's already malaria is saturated over there. There is too much malaria. So we concluded that in this area here of West Africa, climate change is not likely going to make things worse. It may be the same or slightly better. So that was somewhat of good news. So that's really this region of West Africa, where now is the hottest region for malaria. So not all news about climate change are negative. So we think we understand that this hotspot for malaria in West Africa is not likely to get worse in the future. What about regions now where malaria is not that prevalent? For example, let's look at Ethiopia. And so we spent a significant time doing a similar study, also starting with field work, monitoring the environment in this region here of Ethiopia. The interesting thing in Ethiopia is that, if you simulate here the production number for different stations in Ethiopia, you find that, it peaks as expected in this 25 to 30 range, However, Ethiopia has highlands. It has a gradient of temperature conditions. And so unlike West Africa, which is this red line, is all located in this side of the distribution. So when climate makes things warmer, things get better because it becomes more difficult for malaria to get transmitted because you are located on this side of the distribution. Some of the locations in Ethiopia are located to the left of the distribution. So when climate change makes things warmer, it's actually pushing the system into the optimal range. So again, local context is very important. So if you are locally located to the right of this curve, your temperature is warmer than the ideal for malaria. Climate change is potentially good news for you. It pushes things away from the optimal. If you are, on the other hand, located in a region that's now, doesn't have malaria and, things are cooler, like some parts of Ethiopia, then climate change could really push you up the curve, and that basically results in more malaria. You see it here. By doing that, we were able to identify sub-regions within Ethiopia where the conditions are such that things are not ideal for malaria now, but they are going to be ideal in the future with some degree of warming. And we could associate those areas with the elevation bands. So these are basically elevation bands where the temperature is just right for malaria to be enhanced. There are areas in Ethiopia where you already have some malaria, and so those are likely endemic areas in low-lying areas. And then there are areas where even in the future with global climate change and with all the warming, things are cold enough that malaria will not be a factor. So basically, in a way, the belt of land where malaria now exists in Ethiopia would creep up depending on how much warming we produce globally. That belt of land will creep up the mountains, and some of those villagers that have now, colder than what malaria would like conditions, they would be pushed into the ideal range, and those are the people who are going to suffer. And that's where the adaptation and all the resources has to be allocated so that we could adapt better to climate change in that area. So this is again contrasting West Africa with East Africa. That basically gives you an idea about how local context is pretty important. So there is, as I said earlier, there is a whole book on this that you could find in Amazon about projecting the impacts of climate change on malaria transmission in Africa. So this is the third example here. I will stop here. And I think maybe we are getting short of time for the fourth example, unless Lloyd thinks otherwise.
Yeah, well, I mean, if some people, if they can stay, if you can stay, there are a couple of questions if you have time.
Yeah, please.
So what David asks, do you propagate the presumably considerable uncertainty in the numerous modeled coupled components in the hydromats code to provide some kind of posterior predictive distribution?
Yeah, we do. As I said, we spent a lot of time. This is a project that took about 10 years. We spent a lot of time building and testing and validating, different components of the model. We do the hydrology differently. We do the entomology. We test the hydrology and the entomology. We put them together and we look at and test the overall system. And so we think the broad projections that we have contrasting West Africa and East Africa, and how the different conditions over there lead to different outcomes on how malaria could be prevalent in the future. We think that's something that's very robust for this uncertainty.
Okay, and Zahid has his hand raised. So Zahid, do you want to pose your question?
Thanks, Lloyd. Can you hear me?
Yeah, we do.
Okay. Yeah, I was very interested in your malaria in Africa analysis, and one of the things that I have been thinking about, or did think about a while ago, was that I'm situated in South Africa, and obviously it's expected to get warmer here in South Africa due to climate change, and we know we don't really get malaria here, or at least further down South Africa. And the question to you is that with the warming climate, are we expected to become more prevalent in malaria cases as the climate warms in South Africa, I guess?
That's a very good question, and I think we haven't looked directly at South Africa to see how things are going to look like in that specific region. You see it here in the map, not really a hotspot. But I think the question you have to ask is what range of temperature do you have now? Where do you fall where do you fall within this distribution that I showed here? If you are located in this area here, then climate change could really be a problem for you because it could push things into more suitable. It puts you in the ideal range. If I think the good news are for regions of Africa where malaria is very intense already because they are located here. So climate change could provide them a relief by pushing them out of the optimal zone. Regions and sub-regions and localities in Africa that are located on this side, which are, I think these are mostly areas where you have a little malaria, but not much, some marginal, it happens a few years. Those areas, climate change could be quite bad news for them because it would move them right in the optimal range. And so you could think about it that climate change is going to shift this distribution. The marginally suitable becomes ideal, and the ideal they get the relief. So that's what you could generalize from our study.
Okay, thanks, man. That's a great answer. Thank you.
So we're past the top of the hour, but let me ask if anyone else has additional questions.
Yeah, I could actually stop here, Lloyd, if people because we told people there is the story of the Nile, which is another story. But I could stop here and acknowledge my collaborators, the students and funders and so on. And a lot of this information is available in the web in eltahir.mit.edu.
Yes, and I've shared your website with everyone that was on today, as well as those that couldn't make it, but will view the recording later.
Yeah.
So a last chance for any other questions? If not, I want to thank you for the excellent discussion today. Very, very informative on a number of topics that are of keen interest to all of us. So thank you again. Let me go ahead and end the recording.